You can give any location in a city by referring to a street intersection. You'd be using the streets as a system of intersecting lines to measure distances from certain starting places. In pretty much the same way, you can locate the city itself, or any place on Earth, by using a system of imaginary lines on a globe or map, lines of latitude and longitude. To use this system, you need to know the units of measurement and the starting places. Now, the Earth is a sphere, not a perfect one, but very close. And on a sphere, an imaginary line of latitude or longitude turns out to be a circle. The largest circle we can draw is called a great circle. To measure parts of a circle, we use degrees. 1/4 of a circle is 90 degrees. Half a circle is 180 degrees. And a full circle is 360 degrees. Now we need to pick a starting point for measuring. It could be, say, the North Pole, or the South Pole, or perhaps halfway between the poles at the equator. Actually, the starting point is based on observations originally made hundreds of years ago. On the open sea, with no landmarks to help them, sailors could determine their location by noticing the position of the sun. Near the equator, the sun was high in the sky at noon. But when they sailed away from the equator, the noonday sun would gradually appear lower in the sky. So, for latitude, the equator was chosen as the starting point, latitude 0. And other lines of latitude are drawn parallel to the equator. Any place on this line is at 10 degrees north latitude. To see why, we'll cut away a section of the Earth. Now we can measure distance from the equator as parts of a circle. This angle does measure 10 degrees. And this angle measures 20 degrees. All points on this line are at 20 degrees north latitude. We'll draw lines of latitude every 10 degrees until we reach the North Pole at 90 degrees north latitude. It works the same for south latitude, south of the equator. The lines are called parallels of latitude. Now, 10 degrees of latitude takes in quite a bit of territory. To locate a spot more accurately, we can draw lines for each single degree of latitude. But actually, the distance represented by 1 degree of latitude is still fairly large, about 70 miles, or about 115 kilometers. If we really need to locate a spot accurately, we can divide a degree into 60 smaller parts, minutes. Each minute represents a little more than a mile, or a little less than 2 kilometers. And each minute is divided into 60 seconds. The distance represented by 1 second of latitude is quite small, about 100 feet, or about 30 meters. So, by using degrees, minutes, and seconds, we get a pretty accurate measurement of latitude, the distance north or south of the equator. But to locate a place, it's not enough just to have lines of latitude. We need another set of lines to show distance east and west, lines of longitude. Measurement of longitude is actually based on time of day. The Earth rotates through one full circle every 24 hours. So at any given moment, in some places the time is midnight. In other places the sun is rising. And in other places, the sun is at its highest point for the day. That gives us the basis for drawing our lines of longitude. And it explains why a line of longitude is also called a meridian. The word meridian means noon, when the sun reaches its highest point in the sky. That happens at the same moment at every place along the same meridian. We use the meridian passing through Greenwich, England, as the starting point for measuring. It's called the prime meridian. All places on this meridian are at longitude 0. and the distance to any other meridian is measured in degrees. So this meridian is at 15 degrees west longitude. To see how the measuring is done, we'll cut away part of the Earth along the equator. We can see that the angle between these two meridians does measure 15 degrees. By adding another angle of 15 degrees, we can draw another meridian. Measuring from the prime meridian, we're now at 30 degrees west longitude. We can draw meridians for west longitude every 15 degrees until we reach 180 degrees, halfway around the Earth. The other half, of course, is east longitude, measured eastward from the prime meridian to 180 degrees. Now, measuring degrees can be very different from measuring miles or kilometers. Meridians are farthest apart at the equator, but they join at the poles. We've drawn the meridians 15 degrees apart. At the equator, each one of these 15 degrees covers about 70 miles, or about 115 kilometers. But halfway to the poles, each one of these 15 degrees of longitude covers only about 50 miles, or about 80 kilometers. Each degree of longitude can be divided into minutes and seconds. So, by using both meridians of longitude and parallels of latitude, we can pretty accurately give the location of, say, a highway bridge or any other place on Earth. Some maps, by the way, like this one, show meridians as parallel lines, not meeting at the poles, as they really do. But even so, we can still use latitude and longitude to find any location, say a city like Denver, Colorado. Denver is closest to the 40th parallel north of the equator. And west of the prime meridian, on the 105th meridian, Denver, Colorado, latitude 40 degrees north, longitude 105 degrees west. Try another location, Sydney, Australia. Sydney is south of the equator, on the 34th parallel, and east of the prime meridian, on the 151st meridian. Sydney, Australia, latitude 34 degrees south, longitude 151 degrees east. So, using latitude and longitude, we can locate any spot on the Earth. And we can use longitude in another important way. We know that the Earth rotates through a full circle, 360 degrees, every 24 hours. So, in 1 hour, it rotates 1/24th of a circle. That's 15 degrees per hour. So we can divide the Earth into 24 time zones, each one 15 degrees wide. For this system of time zones, the logical starting place is the prime meridian that passes through Greenwich, England, longitude 0. And, in fact, the prime meridian is the center of the first time zone, 15 degrees wide. When the sun has reached its highest point over the prime meridian, that is, when it's exactly noon there by the sun, we consider it to be noon across the entire first zone. The time here is usually called Greenwich time. The meridian 15 degrees west of Greenwich is the center of another time zone. Moving west 15 degrees makes it 1 hour earlier, 11 a.m. in this zone. At 30 degrees west longitude, it's 2 hours earlier than Greenwich. So it's 10 a.m. all across this zone. As we move west, for every 15 degrees of longitude, the time is another hour earlier. So, naturally, moving east will make the time later. If it's noon Greenwich time, then in the first zone east of Greenwich, the time is 1 p.m. For each 15 degrees of east longitude, the time will be another hour later. That gives us 24 time zones, one for each hour of the day, with a meridian of longitude at the center of each zone. But it's not always convenient to follow the meridians exactly. After all, the Earth has various kinds of natural boundaries that don't follow meridians. And there are political boundaries as well. It makes sense to adjust the boundaries of time zones to follow some of these other boundaries. We can show the adjusted time zone boundaries in North America. When it's noon Greenwich time, then in the Eastern Standard Time Zone of North America, the time is 7 a.m. And it's 6 a.m. Central Standard Time. 5 a.m. Mountain Standard Time. 4 a.m. Pacific Standard Time. 3 a.m. Yukon Standard Time. And 2 a.m. in this zone. In Alaska, that's Alaska Standard Time. But in Hawaii, it's called Hawaiian Standard Time. The next zone includes the far western part of Alaska. It's Nome Standard Time, 1 a.m. That's 11 hours earlier than Greenwich time. A little further west, in the region of the Pacific Ocean, we draw a line that generally follows the 180th meridian, halfway around the Earth from Greenwich. It's the International Date Line. By general agreement, this is where we change from one calendar day to the next. So if it's Monday on the east side of the line, it's Tuesday on the west. If you travel eastward across the date line, you repeat a day. And if you move westward across the line, you lose a day. So, using this pattern of imaginary lines to show latitude and longitude, we not only have a way to give the location of any place on the Earth, but also a basis for a worldwide system of time zones.